Hello and welcome. This is Chapter 7, Newton's Third Law, Section 4 on ropes and pulleys. There's one more section in this textbook, or in this chapter, Section 5, but that's just a section with many different examples. And definitely, if you want to learn this stuff, go through all those examples in detail, try and work them out on your own. Some of them will take some time, but they're certainly well worth the time if you want to really learn the Newton's third law. And this section is certainly an important part of that. It's about ropes and pulleys, how we use ropes and pulleys in the context of solving these problems. And so first, we have to go back and remind ourselves what tension is. In chapters 5 and also in chapter 6, we kind of went through a conceptual overview of tension and friction and the normal force and all those basic forces. Well, tension is modeled. We use this ball and spring model, if you remember the ball and spring model from chapter 5, as a way to show that, things that we think are solids really microscopically are modeled as tiny little balls, atoms, connected by spring-like molecular electrostatic bonds. And they stretch and they compress according to kind of the same way that a spring would. And if you look at the microscopic picture of this spring, or this rope, then it's stretching in both directions, right? If you take a rubber band, or if you take a spring or a coil for like putting in the battery or something, you feel a push on both ends. Same thing with tension. You always feel tension. You always feel a pull on both ends. So every chunk of that rope feeling a large pull on both ends, that's what we mean by tension. And in general, actually, the rope, if it's hanging vertically, the tension will actually increase with height. Because if you think about the bottom of that rope only has to support the block. But as you go further and further up in the rope, the higher parts of the rope have to support not only the block, but also all the rope below it. Now, for simple strings and modest sized ropes, that isn't a big deal. When you're dealing with really heavy industrial chains, you want to be aware that the chains near the top are feeling a lot larger of a pull between them than chains near the bottom. So I guess, what's the saying? Every chain, there's always a weakest link, but well, put that weakest link near the bottom so the chain will last longer. Okay, so that's an idea about tension at the microscopic level. This becomes useful, and simple example, it's really thought-provoking. You see two people doing tug of war on the right, and then a single person pulling with a rope attached to the wall. And the idea is that when you first look at this picture, you might be tempted to think, well, it's only one person on the left, so the tension must be less. Or, oh, well, there's two people on the right, so the tension must be twice as more. When in fact, it's the same. The difference is that on the wall, it's the wall that's feeling the force, but the rope feels the same tension. And you have to imagine that there are all these little action-reaction pair dotted lines. In fact, they actually draw them right here. These little action-reaction pairs. The rope, the two arrows on either side of the rope, that's what we call the definition of tension. There's tension in a string when there's an equal opposite force on both ends of the rope. That's what tension is. And that turns out to be the same as for the wall as the person pulling on the, as the person pulling on the other side of the rope. It doesn't matter what agent is applying that force. It's not easy for us to see that the wall is feeling the force because we don't see or feel it. But it's the same thing. So I'm going to finish with that and talk about the massless string approximation. For many of these examples, it will be useful to assume that the string is massless. And what that means is that the tension on one end is the same as the tension on the other end. So it's not what I had said earlier, where the tension might increase as you go low or as you go higher because it's supporting more mass. And typically, again, about 95% of the problems in this textbook use this approximation. There's one or two problems that do not use this string approximation. And in general, if you were to use it, the mathematics would become a lot more complicated. You would need to know the density of the string, and the density of the string would affect the overall motion. So we'll stick with that. We'll stick with this. We'll stick with this approximation. What else? Oops. Let me just look at these over a little bit. To the massless string, those tensions are the same. If the massless string approximation wasn't valid, or if this was like a heavy chain that is approximately the size of those blocks, well then those two vectors in the middle would be different sizes. But again, we normally stick with this assumption in these types of problems. So this is a good example to work out. I'm not going to work out it in detail. Again, this is something that I consider you go on your own. But in looking at these forces, don't draw the interaction diagrams, but so we have M sub B is greater than M sub A. So begs the question, which of these ropes are bigger? Well, there's a T1. And so what does a free body diagram of A look like? You have T1 to the right. You have to have T2 on A pointing to the left, but it has to be smaller. Otherwise, the object wouldn't accelerate to the right. And then T2, barring any friction, is the only force horizontally for B. So again, looking at the horizontal parts, often in these examples, the book ignores the gravity and normal for these types of problems. But once again, we see that the T1 has to be bigger than T2. Otherwise, A wouldn't accelerate to the right. Otherwise, block capital A wouldn't accelerate to the right. And so it seems kind of weird, but make sure you understand this logic. So there's a smaller tension applying a force on a bigger mass, and yet they accelerate at the same rate. So what's the same here? I mean, block A has a bigger tension, and yet it doesn't accelerate more. I mean, because it's smaller mass. You have to make sure you understand that the thing that's the same between these two is the acceleration. And since the acceleration is the same between the two, then block B will have a larger net force. In fact, the net force on B will equal T2, and the net force on A is the difference between T1 and T2, which by definition is smaller than T2. So A has a smaller net force, B has a bigger net force, and yet they experience the same acceleration. Another conceptual thing. And then go through all those examples if you're not clear about it. So I'm going to move on. Pulleys. Pulleys are the next big part of this ropes and pulleys paradigm. And there's assumptions we make on them. So pulleys act as a way to transfer the direction of force applied. Mathematically, you can literally think about it as a mechanism that rotates a vector, rotates the direction of the tension. We usually think of the ropes and pulleys as part of the environment. So we don't think of the internal forces, but a step-by-step analysis on the pulley shows that it feels a tension. Say the pulley, it feels a tension to the left, and it feels a tension downward. If we're looking at this little picture here, in addition to like a small gravity and a relatively large sufficient support force. So the thing with the pulley is, once again, there's also assumptions that we can make about it to make the problem easier. The first one is assuming that it's massless. Why do we have to assume it's massless? When can we assume it's massless? Again, if the size of the pulley is small compared to the size of the object, so it's a fair approximation. It turns out that if you have a very large pulley to rotate, then the tensions on either ends of the pulley will be different. That reason is talked more about in chapter 12. Also, another assumption that can be made about the pulley is that it's frictionless. That's got frictionless bearings, and the rope kind of slides frictionless, smooth on the edges of the pulley. Again, if you don't relax that assumption, then the friction as a whole will contribute to the acceleration of the blocks, not in any real detail that I want to consider here. Once again, chapter 12 handles those types of problems near the end of chapter 12. Okay, and so the last slide in this grid is to decide how you work with ropes and pulleys, because you'll encounter problems where the ropes and pulleys aren't necessarily horizontal and vertical. They might be in different directions. Okay, if a rope pulls on one end of the rope, let's see, the tension in the rope equals the tension on the other side. That's the important thing. And that's really the thing to remember. If a force pulls on, let's see, next bullet, if the rope passes over a pulley, the tension in the rope is transferred in the way that you would expect. And again, the definition of tension still holds in that it's always along the direction of the rope away from the object. So in looking at this example, the hanging mass feels an upward tension force, and the resting mass feels a rightward tension force. But the only way to convince yourself of that is just go through a systematic definition of tension, Newton's third law, definition of tension, third law, pulley, tension, third law, pulley, until you get to these two things. And when you draw these on a free body diagram, Newton's third law holds for them, but they're not necessarily action-reaction pairs. And so what we do is when we draw the dotted line between them, we write something like as if they're action-reaction pairs, just so we know that, well, they're not technically action-reaction pairs. There's a whole environment between them, and there's several AR pairs between them, but these two are the resulting ones useful for the motion. So again, to conclude chapter 7, these can be very involved problems. I encourage you to work with your instructor to go through as many of these as you can. What I found is that when many students really take the time to master this chapter, many different topics that they might have had confusion on kind of blend together and kind of mix, and things finally start to come together in this chapter. So I hope that's the same for you, the same for your case. Go through as many examples as you can and reach out to any of us for as much help as you want. So this concludes chapter 7 videos. We'll start on chapter 8 videos in the next lecture. So again, thanks for your time and good luck with these problems. Take care.